Hello friends, welcome to the online lecture series of St. Andrews Institute of Technology and Management, Gurugram. Myself, Satinder Vats, Assistant Professor in Etce Department, and our today's topic of the lecture is flip-flops. We will study some flip-flops, that is SR flip-flops, JK flip-flops, T flip-flop, D flip-flop, which is a part of digital electronics and telecommunication fourth semester. Okay, so let's start. Today's topic is flip-flop. So first of all, we need to understand why we use flip-flops. So we need to understand sequential circuit first. We have already studied about the combinational circuits. So what were combinational circuits? In combinational circuits, the output depends on the present inputs only. That means what we are feeding to the system, that is the output will depend on that only. It will provide a particular type of function depending upon the inputs. So output depends only on the inputs we are providing to the system. And so what is the difference in sequential circuit and combinational circuit? In sequential circuits or in many applications, we need digital outputs that changes in accordance with the input signal and as well as the past history of input signals. That is, in sequential circuits, output to be generated not only depend on the present input but also on the past history of these inputs. Unlike in combinational circuit, output depends only on the present input. But in these sequential circuits, the output depends on the past history of inputs as well. So how we will provide the past history to our system? So there will be a feedback connection used from output to input. We will feed some part of the output into the input using a feedback connection. So for this purpose, we need a memory element. What do we need? We need a memory element which is used to store the past history of inputs. Okay, so here we can see the block diagram of a sequential circuit. It consists of a next state logic in which we feed the external inputs and the inputs from the memory elements, that is this. So next state logic is fed by external inputs and the past inputs as well that this memory element is stored, and the output logic is depend on the external inputs and the input from the memory element as well. So it will be the external output. So in combinational circuits, our output used to depend only on present inputs, but in sequential circuit the output depends on both the present inputs and the past inputs as well. So this lecture is all about these memory elements. Okay, how we store the past history or past input values in a circuit which is used in sequential circuits. So let's start with the 1-bit memory cell, that is also called latch. So it is basically a digital memory circuit which stores only 1 bit, that is it can store 0 or it can store a 1. There are two stable states of a latch. State 1, that is when it stores 1, and state 0 when it stores 0. So it can be in any one of these two states at a particular value of time. Okay, so this is the diagram of the 1-bit latch. This is a circuit which involves two inverters connected such that the output of one is fed to the input of other. The output of one is fed to the input of other, like that, as we can see in the figure. Output of one inverter is connected to the input of the other inverter. So now let us assume that the initial value of this Q output, that is the output of inverter A. This is inverter A and this is inverter B. Okay, so output of first inverter is Q. So let us assume initially if Q was 1, if initially Q was 1, then it is fed to the inverter, this inverter. So output of this inverter would be, if input is 1, the output would be 0. So if Q is equal to 1, then Q bar comes out to be 0. Similarly, if Q is equal to 0, Q bar will come out to be 1. That is the output of both the inverter would be complement to each other. If Q is equal to 1, then Q bar will be 0. If Q is equal to 0, then Q bar would be 1. So it will remain in one of these states. If it has two stable states, Q is equal to 1 and Q is equal to 0. So Q is equal to 1. If Q is equal to 1, then it is referred as set state, and if Q is equal to 0, it is referred as reset state. If the circuit in state 1, if this circuit we have just seen is in state 1, then it continues to remain in this state, and if it is in 0 state, that is reset state, it will continues to be in 0 state, because there is no provision to change the state, because we cannot apply any input to it. If it was Q, we don't know what it was initially. If it was Q is equal to 0, then Q bar will be 1, and if Q is equal to 1, Q bar will be 0. But we cannot provide external input. There is no provision as such in this latch to provide an external input, so that we can change the state according to our function. So that's why, as we can see, since the information is logged, this information is logged in it. Since the information is logged or latched, the circuit is referred as a latch. Logged means latch. This bit information, that is, if a 0 is stored or a 1 is stored, it is logged in this circuit. We cannot change it by providing any input there, because there is no such provision. Now let's move to the next thing, which is the SR flip-flop. It is nothing but a advanced version of that latch we have just studied. In this latch, what we can do, it will also store only one bit of memory, that is 1 or 0, but we can provide inputs to change that state from 1 to 0 or 0 to 1. We can provide external inputs to this circuit, which can change the state from 1 to 0 or 0 to 1. This is the basic difference between a latch and a flip-flop. We cannot provide external input to the latch, but in flip-flop we can do. Okay, so this is a SR latch or SR flip-flop we have implemented using NAND gates. So in latch we have only two inverters. Now in SR flip-flop we have used two extra NAND gates. So circuit will look like this. Okay, so these are the two input NAND gates and these are the inverters. Okay, if we provide these inputs like S is equal to 1 and R is equal to 0, the output of G3 inverter would be 0. If S is equal to 1, this would be 0. If R is equal to 0, this would be 1. So this would make Q is equal to 1 and Q bar is equal to 0. Q would be 1 and Q bar would be 0. Okay. Similarly, if we provide S is equal to 0 and R is equal to 1, this will make Q is equal to 0. Okay. If we provide S is equal to 0 and R is equal to 1, so Q would be 0 and Q bar would be complemented of Q, that is 1. So this condition S is equal to 1 and R is equal to 0 makes Q is equal to 1. So it is referred as set state. If S is equal to 0 and R is equal to 1, which makes Q is equal to 0, it is referred as reset state. Now if both the inputs are 0, that is S is equal to 0 and R is equal to 0, what would happen then? Let's say if it was in one of these states before and now we have changes the inputs to S is equal to 0 and R is equal to 0, then output would remain unchanged and continues to be in the previous state. If for this combination S is equal to 1 and R is equal to 0, our Q value was 1. Now if I change both the inputs to 0 0, it will continue to be 1. And if it was 0 1, okay, and then I change this to 0 0, then Q will continue to be 0 and Q bar would be 1, because for 0 1 it was in reset state. Q was 0 and Q bar was 1, so it continues to be in this state if inputs changes to 0 0. Okay, and if we provide both the inputs S is equal to 1 and R is equal to 1, what would happen? The Q and Q bar both will try to become 1. If I give both inputs 1, then Q will be 1 and Q bar will also try to be 1, which is not possible at Q and Q bar are complemented of each other. So this state is not possible. So this condition is prohibited in SR flip-flop. So now next is clocked SR flip-flop. In clocked SR flip-flop, we will provide a clock signal to our SR flip-flop. That means it will change its state, or we can save any state that is 0 or 1 into the flip-flop only when the clock signal is high. If clock signal is 0, it will continue to be in the same state. That means we cannot change the state whatever the input we provide to the SR flip-flop. It will only change when the clock goes high, that is at clock is equal to 1, then its operation is exactly same as the unclocked flip-flop. If clock is equal to 0, then the gate Z3 and Z4 are inhibited, that is their output are 1 irrespective of the SR inputs. So if their outputs are 1, if their outputs are 1, okay, if clock is 0, the output would be 1 and 1, so it will not work. So it will only work, or the state would be changed when the clock signal, when our clock signal is high. So this is the difference between a simple SR flip-flop and the clocked SR flip-flop. We can feed the data into the flip-flop according the clock pulse. If we provide a high pulse, then only the changes state will take place. Okay, so we can see here the truth table of SR flip-flop. It is nothing but what we have seen. We have just arranged these results in a table. So this is the truth table. If S and R both are 0 0, it will continue to be in state previous state. If it was 1, it will remain in 1. If it was 0, it will remain in 0. So no change of state will take place if the inputs are 0 0. Okay, now if the inputs are 1 0, then the next state Q1 plus 1 would be 1 irrespective of the previous state. If we provide 1 0 as input, if it was 0 previously, then it will become 1, or if it was 1, then it will remain 1. Okay, similarly, if we provide 0 and 1 as S and R, then Qn plus 1 would be 0. So if S is 0, the output Qn plus 1 next state will be 0. If it was 0, it will remain 0. If it was 1, it will change to 0. Okay, and 1 and 1 is prohibited. Okay, it is not valid in SR flip-flop because both the inputs, both the outputs Qn and Q bar will try to be high. So Sn and Rn denotes the input, Qn plus 1 is the next state, and Q1 was the previous state. So if 0 0 is there, it will remain in Q1, that Qn, that is the previous state. If 1 0 is there, it will change to 1. If 0 1 is there, it will change to 0, and if 1 1 is there, it is undefined. If S R both are 1, then next state is undefined. So next is JK flip-flop, in which we can use that condition of S is equal to R is equal to 1 as well. So the uncertainty in the SR flip-flop when both the inputs S and R were 1 can be eliminated by converting it into a JK flip-flop. So how we'll convert it into a JK flip? We will use 2 extra NAND gate, AND gates. So this circuit is same as the SR flip-flop. Now we will provide the inputs J using these AND gates, as we can see over there. This is the S, this is the R. So S is coming from a AND gate, which is nothing but the product of J, that is J input, and the Q bar output. Similarly, R is nothing but the K multiplied by Q. Thus, K is the input and Q is the output of our SR flip-flop. So this is how we can make the JK flip-flop, in which what we have, S is equal to J into Q bar and R is equal to K into Q. So to implement this, we have used 2 extra AND gates. So that's how, so that we feed the input using these extra AND gates. Now see how it changes the table. Look at here. Here we have 4. If the clock is high, if it is a clock signal, as we are already seen, if clock is high, only then the change would be there. State would change. If j is equal to 0, k is equal to 0, it will remain in the state qn. If j is equal to 1, k is equal to 0, then it will be in the set state, that is next state would be 1. For 0 1 it would be 0, and for 1 1 there is a change. Now the state would be complement of previous state. If we provide j k both 1, okay, then the output, that is qn plus 1 next state, would become qn bar. If it was 1 previously, then it would change to 0 on providing the input 1 1. If it was 0, it would change to 1. So it will toggle, or it is not exactly toggle. We will see that it will race around when the input is 1 1. Let us see how. If we provide both the inputs, what is racing? This is a question which oftenly comes in our semester exams. So what is the race around condition in JK flip-flops? If we provide both the inputs J and K is equal to 1 and clock is high, okay, we have provided both inputs high. So Q, what would happen to Q? Q will be 1, then it will change to 0, then 1. Similarly, Q bar is 0, then it will change to 1, then 0, and then 1. So it is a different thing from toggling. Toggling we will see in the toggle flip-flop. What is toggling? We can correct this race around condition also. We will see in the next lecture that how to correct this race around conditions. So what is race around condition? If we provide both the inputs j and k is equal to 1, then q and q bar will start racing around from 1 to 0 and 0 to 1, 1 to 0 in the same clock. If clock is high, then qn is high, then 0, then high, then low, then high. In the same pulse, it would keep on changing. The output will keep on changing when k is equal to 1 and j is equal to 1. This is called the race around condition, when output keeps on changing. Okay, now let's see two more flip-flops. The next one is D-type flip-flop. It has only one input, that is D, data, which is called data input D. That is why it is called D-type flip-flop, and it can be made using JK or SR flip-flops. We can actually convert all these flip-flops from one to another. That we'll see in the next lecture, how to convert one flip-flop to other. For the time being, let's see the D flip-flop. What is a D flip-flop? So we can, here we have drawn the circuit of D using JK flip-flop. Here in this one, what we have done, we have made it using JK or SR flip-flop. So if we provide, like, if J is one input, then what we will do with K, we will provide K is equal to J bar. That is, we have complemented the two inputs. If one is K, then other would be K bar. Okay, K is equal to J bar. If it was J, then we have put a inverter over there, and the other input would be J bar. So we are providing only one input, and the other would be the complement of it. We are providing only one input, one end of the JK flip-flop, that is D, and for other input it would be the D bar. So we have only one input in D-type flip-flop. And what would be the output. If D is equal to 0, then the next state Qn plus 1 would be 0, and if D is equal to 1, the state would change to 1. That is, whatever we are providing at the input, we are getting at the output. The state changes to the input, whatever input we are providing. So state Qn plus 1 is equal to D. Whatever input we are providing, it is reflecting at the next state. Okay, now next is T-type flip-flop, that is toggle flip-flop. What in like in D-type flip-flop, we have complemented both the inputs, but in T-type what we would do, we will short them, both the inputs are same. Okay, so in T-type, if we make it using JK, we will short the inputs. J is equal to K, both the inputs are same. So when the input is 0, the output would be Qn, and if input is 1, then it will be Qn bar, that is toggle. If it was 1, it will become 0. If it was 0, it will become 1 for Tn is equal to 1. At the input 1, our next state would be the complemented of the previous state. Okay, so this was for the lecture. I hope you understand the basic flip-flops, their truth tables. Okay, thank you very much.